it for actual manufacturing, and it was so called as rapid manufacturing. And there are so many names that are there for 3D printing. So you can also say it as layered manufacturing because the parts are produced by layers. So there are different names in which this process is actually called. And also you can see the bioprinted tissue. Uh, so this actually demonstrates how 3D printing can extend beyond prototyping in the healthcare applications. And there are some potential advantages, or you can say benefits of the 3D printing. So we have sustainability. So sustainability is like where we have reduced waste when compared with the conventional manufacturing methods, where we use only materials when it is needed. So it's about material efficiency, and also there is a reduced energy consumption. And then the next one is the customization. So each part can be unique so that you don't have to spend too much of no money on tooling and other things. And also it's very critical for making personalized medical devices, hearing aids or dental implants. And it's about mass customization, how you make unique parts at a time. In a build, you can build customized parts together, so it saves a lot of time and money. And then innovation in healthcare, it's about making surgical planning models, and it could be patient-specific implants, which is again the customization. And a very good example for it is the bioprinting. So a lot of research works is going on in bioprinting. And then it has a benefit of making complex designs. So we can manufacture geometries which are impossible in conventional methods. So for instance, you could take ladder structures, or if you want to really make organic shape products, or you want to build a product which has got internal channels, like where you have this molds and dies. So where you have very complicated internal channels that could be easily printed in 3D printers, and which is impossible in conventional manufacturing methods that could be done in the 3D printing technology. And then rapid prototyping. So as I said, during the invention of this particular technology, it was called as rapid prototyping. So it accelerated the product development. So iterations from the concept to the physical prototype, which were made in hours. Previously, it was taking weeks to get it done. So it was reduced to hours, and we had a reduced time to market. And then cost efficiency. So it is like eliminating the tooling cost and the material waste, so that making the small batch economically viable, and also low barrier to the entry for startups or any enterprises. And the last one is about the supply chain flexibility. So it's like printing on demand whenever it is needed, so that we would have reduced inventory, and also it helps to deal with the logistic complexity. So basically, it is about decentralizing the production process. So these are the potential benefits of the additive manufacturing. And as per ASTM, American Society for Testing and Materials, we can classify the additive manufacturing process into seven. So this is according to ISO ASTM 52900. So the first process is VAT photopolymerization. So it actually works based on the light source, let's say a UV laser, or it could be a DLP projector. This is a digital light projector, which actually selectives, and it actually cues the liquid resins layer by layer. The material predominantly that is used in this process is photopolymers, and it's actually suited for high detail, smooth surfaces, especially in jewelries or dental models. If you want to make some prototypes, there you can go for this particular process. And the key advantage of this process is it's got highest resolution and surface finish among other processes. And then the second one is about the powder bed fusion. So here, the heat source could be laser or electron beam, which melts or sinters the powder particles selectively. And it generally uses metals like titanium alloys or aluminum, steel, and so on. And also, not only metals, it is also about polymers and ceramics. And this particular process is actually suited for making aerospace components, medical implants, and also making some functional prototypes. And there are different processes under it. Like we have LPBF, which is laser-based powder bed fusion process, and then we have EBM, electron beam melting, and then we have SLS, SLM, that is selective laser sintering. So the key advantage of this process is like it creates strong, dense, and production-ready metal parts. And next process is about metal extrusion. So here it uses the heated nozzle, so where the uh, molten thermoplastic filament melts and then it actually builds up this layers. So the material what is used in this process is PLA, ABS, PTG, nylon, and even we can use carbon fiber composites. And again, it's used for making functional prototypes, tooling mechanical parts, and also, let's say, educational models. And typically, you can find these machines in many institutes. Even in schools, you could find this machine because it's very cheaper when compared with other process machines. And the key advantage of this particular process, it's like I said, it's most affordable and it's easily accessible, and it's widespread in different academia as well as the industries. And next process is about metal jetting. So it involves tiny nozzle sprays, the droplets of build materials and support materials, which is cured with UV light. It is similar to that of VAT photopolymerization, where it again uses photopolymers. Not only photopolymers, it also can use waxes. So it's used for making multicolor parts, let's say complex designs with details. So those kind of things can be done. And the key advantage of this process is like we can do full color printing with no extreme precision. And also we have a lot of variety that could be brought in a single bit. And then binder jetting process. So it's about where we have the print heads, which actually deposits liquid binders onto the powder, so which tends to bond the particles selectively. So it's like the powder bed fusion process where you have powders with lasers and electrons. So instead of lasers and electrons, here you have the liquid binders, basically the adhesives to glue the powders together. And the material that is used in binder jetting is sand. You can use metals, ceramics, and also some polymers. So it's best for making sand casting molds, and then metal parts also you can make. And like I said, you're using liquid binders, so where you can bring in colors. So full color models you can do, and architectural models. And the key advantage of this process is like it's fast and it is cost effective for making very large parts. So that it's like in LPBF, it involves sintering, basically heating. But here it's not about heating; it's about gluing. I mean, how the powders glue each other to make up the product. And next is the sheet lamination process. So it's about thin sheets of no, materials that are stacked and it's been bonded, let's say by means of adhesives, or it could be means of fusion. So where you have this process called ultrasonic consolidation. And it's kind of a hybrid process. If you say it as a metal process, especially this ultrasonic consolidation, it's a hybrid process where you just fuse the metal foils and then cut it using CNC cutters, where it happens in layers. So here the material what predominantly used in sheet metals are, I mean, sheet lamination are paper, plastics, and metal foils, and also you can go with composites. And it's again best for large parts, and also for the composite structures, and also you can use it for prototypes that needs internal geometry also. So the key advantage of this is like large scale parts can be produced economically, and it's excellent for architectural models and composites. And the last process is the direct energy deposition process, where it uses high energy beams. It could be a laser or an electron, and it can melt no materials, let's say wire or powder, and then it deposits on surface. It's kind of a laser welding if you're going in for laser based source. And here the material that we use for this process is metals. We use superalloys and ceramics. And mostly it is used for refurbishing or repairing process. So if you want to deposit material on existing parts, and if you really want to make a large thin wall parts, aerospace kind of parts, then you can go for this process. And it's perfect for making repairs and building into the existing components and also handling exotic materials. So next is about the additive manufacturing applications. So here you can see that the market share of the AM application in various industries. So the majority of percentage goes into the aerospace, so where they use it for weight reduction, precision, and performance. And second goes the medical and dental application, so where it is used for making patient-specific implants and surgical guides. A lot of customization can be done. And then automotive, which contributes 50%. So, I mean, for automotive industry, it's like 15%. So mostly it is used for making prototypes and for tooling and also making some customized components. And then 10% on consumer products like watches, eyewear, or personalized goods. So it's about the mass customization, like I said. And then we have the industrial tools like where you can make customized fixtures, jigs, grippers. So where it can be done at faster pace. And rest is like 15%. So it's about food, fashion, sports, defense, electronics, and so on. So now we would like to focus on the application of AIM in healthcare industry. So this is one case study. So where a silicone artificial heart has been 3D printed, and it was actually done at the functional materials laboratory. So they have fabricated this particular art, and the structure was evaluated with the help of product development group at ETH Zurich in Switzerland. And this is one case study. And also you can see that the additive manufacturing technology is being used for making surgical models. Like you could see, it's used for making skulls with vascular cracks. This is done using 3DP technology. So the surgeons can see exactly where the arteries run before making the first incision. And then the second one that you could see is the bone tumor that's been highlighted in some color to basically indicate there is a tumor. And then we have the vascularity inside some organ where the blood vessels are being revealed. So we are looking at internal structure of a human organ. So this guides the surgical planning. And like on the right hand side, you could see multi-material and multi-color printing. So like you have organs with vascular system, which is shown in red in color, which gives us a understanding of blood flow. And then we have this blood vessel network, which is in red color again. It shows the 3D visualization of the circulation. And then brain section structures with color codings, like different regions have been differentiated. And then we have the brain cross sections with different color mappings showing the functional regions. And then we have the vascular structures. And also we have brains with blue arteries. And next case study is about the titanium mesh that is actually formed around maxillofacial model. So on the left, you could see a CT scanned skull where it is showing the defect and the bone structure. You can see the complexity of how it has been constructed. So it's actually a patient-specific model that has been printed from the CT data. So where the surgeons use it for pre-planning for the exact placement of the titanium mesh. So this titanium implants has to be positioned properly during the surgery. So they have to print the model and then position it accordingly, and so that there is there is no guesswork that is done during the surgery. And on the right hand side, you could see that the biocompatible titanium that has been formed to match the patient anatomy. And also you can notice there are some lattice structures. So this actually provides strength while minimizing its weight, and it's also meant for customized fit, and it's patient specific, and it's been ready to implant. And similarly, you have jaw implant. So this again is made of titanium. So the surgeon actually uses 3D printed guides to position the titanium implant with, let's say, millimeter accuracy. So here again, there is no guesswork or no improvisation. It's completely a pre-planned blueprint. So, and then you can see that the model has been printed from the CT scans, and the implant has been positioned and it's been verified on the model. It's been thoroughly verified whether where it fits. So like you could see in the image, and also you can see that they've been functionally and aesthetically it has been restored, where the jaw structure has been reconstructed and it's been aligned perfectly, and it has been the integration has been optimized so that you could see from these images. And next is about the drill guides. So again, we need to take the CT scan of the patient jaw. So where the digital scan actually captures the bone density, nerve positions, and even sinus locations, everything that the surgeon has to know before the surgery. And this data becomes blueprint for the surgical guide. And like you could see, there is a 3D printed model where you have this 3D printed guide in place. So you can see that some drilling is going on through some guide sleeves. So this drill cannot deviate. So there are some guide constraints to position the drill at a pre-planned angle and depth. So it should be placed perfectly. And you can see that there are some components that are dealt here, like you have depth calibrated drill. So this is for marking the exact drill depth. There should not be any guessing or any over drilling, because you have a nerve underneath, like you have a nerve called alveolar. So it's actually a nerve which you should not touch during the surgery. It can cause excruciating pain, and even it can cause fatal death. So you have to be very careful while performing the surgery. So we need to have this guiding system to basically to avoid that. And then we have the integrated drill key. So this locks the drill in the correct position and makes it impossible to slip. And then we have the cylindrical metallic tube. This actually guides the drill with zero deviation, and it's been serving as a very precise sleeve. And then you have a side entry slot. So this allows the surgeon to position and seat the guide accurately. And then we have the tooth supported 3D printed guide. Like, so this is just on the tooth surface for stability and accuracy. And then we have bone supported 3D printing guide. So this is for the cases where the bone is the anchoring point. And also we have the mucosal supported 3D printed guide. So this is for softer tissues only. So anchoring in very challenging anatomy. So next is about a 3D printed plastic top of a human skull. So this skull is actually lightweight, it's durable, and it's biocompatible. It's made of polymethyl methacrylate. So it's done with a geometry precision that exactly matches to the patient's skull. And you can notice the curvature that has been generated from the CT's curve, that which makes it fit exactly to the skull. And you can see the structural pattern is done for higher strength and lower weight. And at the bottom that you could see that the implant has been placed where it is restoring the skull shape, and also you could see the tissues that integrates with it. And we have a surgical tape that holds everything while the healing actually begins. And this is about customized prosthetic limb printing. So here you can see a lot of prosthetic limbs, customized prosthetic limbs. It's a community where they print these limbs at free of cost. So there are around 1,000 plus volunteers and who have their own 3D printers. So they make customized fitted limbs, and it actually costs zero cost to the families, and it's a big community. So it's a 3D printing community again. And these are the metal implants which have been printed in 3D printers. I mean 3D printing technology, especially the metal-based technology. So we'll start off with the skull. So where we have this customized uh, cranioplasty. So it's basically a patient-specific geometry that has been gathered from the CT scan. And then we have this scapula, so which is the shoulder blade reconstruction, where you have this complex curve geometry, which is impossible to handcraft precisely, which can be done in 3D printing technology. And then we have this acetabular bone, which is basically the hip socket implant. And you can notice that there are two sides for this acetabular bone implant. So one side is fabricated or manufactured with rough surface, and the other side is smooth. So rough side is for the bone integration to happen, and the other side is for the fixation. Anyway, we'll discuss more in detail when we discuss about the DFAM applications. And then we have this knee joint. So it's about total knee replacement. So it's been printed using powder bed fusion process, and it actually produces the strength required for load bearing joints, especially on the knees. And we have lower jawbone, so where you can make customized jaw reconstructions, so which fits the patient anatomy, and it's not like the off-shelf approximation. And then we have this sternum, which is the chest bone replacement. So you can see the internal structure that has been optimized for strength and the minimal weight. And then we have spine of vertebrae, so spinal implants. So there you could see that there are some lattice patterns. So this actually enhances the osseointegration, the way the bone grows into it. And then we have the osteotomy, so which is like a bone cutting guide for constructive surgery, and it's where we have this 3D printed metals, ensuring surgical precision. So this is about 3D printing technologies in different medical applications. So like you could see in dentistry, it's about restorative therapy, surgical guides, and then making dental models. And there are some technologies that are used under this dentistry. It's about the VAT photopolymerization, or where we have this SLA or DLP. And then in the in anatomical models, where we can use it for surgical guides. So if we want to perform any complex procedures, so we need to uh, print a complex model, and then we need to get trained in it, and then have to go for the surgery. So this is predominantly done in powder bed fusion process or VAT photopolymerization. And if it is the actual implant, then we'll go for powder bed fusion. And if it is going to be a model, a simple model, then we may have to go for VAT photopolymerization process. And then pharmaceutical application, you could see that it's about the control drug delivery systems, or no, customized formulations and so on. So this is predominantly done using material extrusion process or bandage-jetting. And then we have this medical devices, so like surgical tools or prosthetics and so on. So which could be done using polymer-based printings like that photopolymerization and metal extrusion process. And if it is going to be metal, then probably we have to go in for LPBF, laser-based powder bed fusion process. And then tissues and organs. So this is about bioprinting, and also it's about the disease models. So here we can go in for VAT photopolymerization and metal jetting. And at the bottom, you can see the technologies that are involved, like what I've discussed. It's about the stereolithography, or you can say VAT photopolymerization. So it is used whenever there is high detail and precision is required, and it's meant for polymers. And powder bed fusion, so mostly it's used for metal implants, and even you can use it for polymers, especially if you want to make nylon models. Mostly they make very strong parts. And then we have this metal extrusion or FDM, fused deposition modeling. If you want to make prototypes at a lower cost, then we can go in for this particular process. And the last one is, I mean, we have this metal jetting process where if you want to go in for multi-material or color printing, then we can choose this process. And the last one is the binder jetting. So binder jetting is for making a large and if you quickly want to make a part, then you can go for this binder jetting process. So this is the process chain that is involved in additive manufacturing process. The first one is the CAD model. So if you take any manufacturing process, it normally starts with the CAD model, or you can say it as 3D model creation. So you have different CAD softwares to make 3D models, or you can go with some reverse engineering process like using 3D scanners. If it is medical application, we can go in for CT scans or MRI scans to get the 3D print 3D models. And then we have to convert a 3D model to a form or a format. We call it as STL. It's kind of a language where the 3D printers understands. So it's like tesslating the model. So where you convert, whenever you convert a model into STL, you could see the faces to be tesslated where you have triangulation that is happening. And then we have to transfer the file into the machine. So before transferring, what you have to do is you have to use some data preparation software. So, or we can say it as slicing software. So where we define different parameters like how we orient the part and how we generate support structure and how we slice the part, like what is the layer thickness that we need to define for the slicing, which defines the accuracy of the print. So those kind of parameters that we need to define in the slicing software. And once it is sliced, we will generate the path for printing. So that path could be in form of some formats, let's say G codes. So which has the path in which the tool has to move to get the model to, I mean, the part to be printed. So that will be transferred to the machine. In machine, we have to do some setups. Like let's say in powder bed fusion process, we basically preheat the bed. So we have to do some preheating, and also we need to ensure that we have sufficient powders for printing. And it could be vary across different 3D printing technologies. So if it is FDM, we need to make sure that we have filament, and we need to preheat the nozzle or bed. So it again depends on what material we are actually processing. Likewise, different 3D printing technologies will have different initial setups that is required for uh, printing. And then the actual build. So where the actual build happens, like it starts to print in layers. So layer by layer, it starts to print, and you'll be getting the final model. And once the model is printed, let's say you could see that the part has been printed on a bill plate. So the part along with the bill plate will be taken for the part removal. So where the part has to be removed from the base plate. So usually it is done using EDM, electrode discharge machining. So once it is removed, it will be subjected to some post processing. So because we have some drawbacks in additive manufacturing, it lacks the surface toughness or the tolerance that is required or demanded by the industries. So we'll have to do some post-processing like anodizing or preheating, like heat treatment processes and sandblasting and so on. So there are so many processes that are involved. And again, it depends on what material you're processing, whether it is metal or a polymer or a ceramics and so on. And then once it is post-processed, it will be taken into the actual applications. Like you could see the actual application here is the vestibular implant. So that you could see it's been implanted on the patient, so which is shown in an X-ray view. So next is about preparing 3D model for additive manufacturing. So the first method uh, how we can come up with a 3D model is using CAD softwares. So there are so many commercial CAD softwares and also open source CAD softwares where you can use it for preparing 3D models. And mostly these commercial softwares or open source softwares are used for making regular geometries which are well defined, which is parametric. So if it is of that kind, we can go for this particular method. If the model is too complex, it's of organic and it's very hard to reproduce or something. And if it is, uh, let's say, a vintage or an absolute part, if you want to basically uh, recreate it, so then we can go in for the method called 3D scanning. So this is basically a reverse engineering process. So where it involves different 3D scanners. Like you could see, we have desktop scanners, which are very compact and it is actually affordable also. Where you have to point on the object, where it captures the point clouds, and from which you create a 3D model. And if you take medical applications and if you are really interested in capturing the internal structures or internal organs, then we can go in for MRI or CT scan. So mostly CT is preferred. So using that sliced images, which we say as DICOM. So DICOM images where you have the sliced X-ray images, which would be stacked upon to create a 3D model. And there are some softwares to basically do the conversion from DICOM to STL or OBJ. And then you have a very simple method where anyone can actually do it using a mobile phone. There is a concept called photogrammetry. So where you can use your smartphones to capture photos and across different angles. So more photos that you take across different angles, and then if you put it into a software, it actually creates a 3D model. So that is what we say it as the photogrammetry. And below you can see different 3D scanners. So like you could see that you have handheld scanners and you have Kinect style camera scanners where it captures real time 3D data. And then we have projection based scanners also where we have the David SLS scanners. And obviously on the right, you can see the MRI and CT scanners. So this is one mm, example of how we can come up with a 3D model using CT scanner. We can see that we have a CT scanner with the sliced images. So where it shows the cross-sectional X-rays of the patient anatomy. So each slices that you could see, it actually reveals the internal structure. And also you can see different views of it. It's about sagittal, that is side view, or axial, or the corneal, or the front view. So where these slices are put together to come up with the model. And you can also see there are a few more examples that has been shown in this particular slide, where you can see on the right, it's about creating a lung 3D model. So where the surface reconstructions, has been done from the CT scanned images, and you can see the accuracy, and you can see some color things also to show the difference. And then you have this lung that has been extracted from the CT data, so which is uh, printed using multi-material printing technologies. So this is like you have different things that has been captured while scanning. It's not only the lung that you capture; it's also about the neighboring regions that you capture. So you basically have to segregate it, segment it, and then you have to come up with this particular model. So there are softwares that helps in doing it. So for example, you have softwares like Metalize Mimics, 3D Doctor, and Amira, Simpleware, so on. And if you are really interested, if you want a free software, an open source software, then you can go in for a software called 3D Slicer. So anyone can use it for free. So this is the tested 3D model. Like I said, whatever 3D model that you have to convert that into STL. So once it is done, you have this tessellation. So more number of triangles, higher is going to be the resolution of the model. So but again, if you have too many triangle, it makes the file size very high. So you have to optimize it accordingly, and then you have to go in for the 3D printing. So now we will discuss about the DFAM methodologies. Sorry, DFAM. Before that, we'll discuss about design for manufacturing. So how it has evolved from design for manufacturing to uh, design for additive manufacturing. So we'll try to understand that. So in design for manufacturing, you can see that there are three drivers. The first one is development of new materials, and then we have the improved design methods, and we have the increased societal demand. So what is the purpose of development of new materials? So when new materials comes, that actually enables that no, makes the designs that were impossible before. And then improved design methods, it's about no, going in for CAD designs, or you can go in for some advanced design methodologies like topology optimization, like weight reduction, and you can go for latticing. So these softwares helps us to design the part in a very smarter and a faster way. And then increased societal demand is about the customization. As a customer, they expect a product to be unique and it has to be specific to the user. It's about customization, and also it's about custom sustainability, and it should be of lightweight. So as you could see in aerospace or automobile, where it demands for lightweighting. So all these things has to be done. And these are the three drivers for it. And you can see the cost reality. So like 70 to 80% of cost goes in design, and 20 to 30% is about the the manufacturing. And this is the time that has been taken, and it's the cost that is involved in it. Like you could see for the concept and design, the cost that is involved is less. So any mistake that is done at design phase, if it has to be corrected during the course of manufacturing, it is going to cost us high. So we have to be very careful while coming up with the final design. So we have to design it in a way that it actually suits the manufacturing process. So what first we have to decide what manufacturing process. I mean, we have to design, and then we have to think about the manufacturing process, and then we need to rethink whether the design actually suits for the manufacturing process. If not, again, we need to iterate the design, and then we have to do it accordingly. If not, we have to read the price if we are going in for redesign. So these are the rules that are there for design for manufacturing. These are common rules across different manufacturing processes. The first one is minimizing the part count. Like how we can minimize the part count. So this can eliminate assembly or the cost related to the assembly. So how do we consolidate parts so that it becomes easy for us to do? So for example, you can take dental implants. So where you have this screw, post, and crown. So instead of printing, instead of manufacturing these components separately and then assembling it together, we can just make it as a single component where it is consolidated from three to one part. And then use of standard parts. So we don't have to reinvent fasteners. So fasteners are something which has standard parts. And also we need to use off-the-shelf screws, brackets, or connectors. So where the customized parts that we use can be expensive. So where standard parts could be cheap, and it's because that they have been produced in mass productions. So that's why the cost is low when you go in for standard parts. So when you can customize the geometry, then you can do it, and you don't have to no, redesign the standard parts if it has already been existing. So we need to think about which part to customize and which not to. And then next is about creating modular design. So it's about building modules of blocks. So each modules that can be manufactured and it can be tested. So if in case any of the module that fails, it can be swapped or it can be replaced. So you'll have that flexibility. Like I said, if any one model fails, you can just replace it, and the rest will not fail. It will be intact. So it is easy to manage if we go in for the modular design. And then design part with multifunctionality. So let's say we have five different components, and instead of having it as five different components, we can try to integrate and then make it as one part where it can perform the multi-functions. Let's say the functions of five components. That is what we say it as the functionality. It's about the functional complexity. So there are different complexities that are there in DFAM. So this is one complexity which we call it as the functional complexity. So this can make the component lighter and can make it stronger. And also we'll have minimum number of parts, eliminating assemblies. And also the main highlight in this is the failure points. So you will have very few failure points if you're going in for the integration. And then design for ease of fabrication. So how we can design a part no, in a easy way. Like let's say, let me take 3D printing technology. So we have to think about printing parts without support structures, and how we can orient the part optimally, and how we can avoid this thin walls or unsupported overhangs. So, and how do we make choices to basically reduce print time and also the material waste that is involved. So those kind of things we can bear in mind during the design phase. And then minimize the assembly directions. So it's like um if you're trying to design a part which is rotating at different angles, so it means that we are actually overcomplicating it. So we need to design the part that actually snaps together, slide into a place, or click from one directions. So we have to make the assembly steps to be fewer so that the assembly can be done at a faster rate, and also we'll have fewer errors, and also it can reduce the labor cost. So we need to minimize the assembly directions. And last is about minimize handling. So every part that has been picked up, moved, or oriented, so it actually increases the cost, and also the risk uh, involved will be high. And we need to design parts that actually stay in a position. It do not actually tip over, and it should be stacked very safely. So it basically reduces the touch points and also the complexity and labor. So that is the purpose of minimizing handling, and that has to be taken care during the design phase. And next is about digital manufacturing. So this is the manufacturing for thing which is about the computer control ecosystems, where the machines can read the designs and it can produce the parts in hours. Previously, it was taking weeks to make it. It's like from CAD to part, so digital end to end. So that's what we say it as Industry 4.0. So it's actually an integrated approach, which is actually centered around a computer system where the machines can actually read the CADs directly and it can deliver the finished parts in us. And there is no tooling or no setup delays or there is no intermediates. It's pure digital to physical conversion. So like you could see in this Industry 4.0, like we have the automated robots, which is meant for handling, assembly, and finishing. So all are automated based on the digital instructions, and we have Internet of Things. So this is like machines can talk together. I mean, talk to each other, and also sensors can track each step, and it can get the real-time data flow. And before we want to, you can go in for simulation. So before, if you want to print a part, you can basically simulate the build and anticipate the issues where the printing can go wrong before getting into the actual manufacturing process. And then next is the big data. So this is like tracking every print, every failure, and also the successful prints. So this helps to learn and optimize the printing process continuously. And then we have this cloud computing. So it's like designing files that can be accessed in the cloud. Like you can access it anywhere. You can do the printing anywhere. And then, of course, the 3D printing technology. It's a core technology that helps to convert the digital files into the physical parts. And then we have augmented reality. So it's about visualizing the part before printing, and it helps to collaborate across different teams virtually. And then we have cybersecurity, which is to protect the design files and also prevent unauthorized no manufacturing and also secure supply chains and so on. And the last is about the automated quality. So where sensors actually verify dimensions, it can be used for verifying material properties, surface finishes. It can be completely automated. So additive manufacturing, what you see is what you build. So whatever that we are visualizing, that can be literally printed. It can be manufactured, is what it means. So it's because that we are able to print it in layers. So that's why the complex geometrical complexity is less in additive manufacturing when compared with other processes. So why we have to go in for DFAM? So we have come to a conclusion that we have to go in for additive manufacturing. Then if we have chose additive manufacturing process, then why we need to go in for additive, I mean DFAM? So there are two obstacles that we see here. 71% it's about lack of knowledge. So many companies don't know how to use 3D printers effectively, and they don't understand what is DFAM. So it's like designing specifically for the process. So they think in a traditional way. So thinking about CNC compatibility, if it is injection molding, it's about molding friendly and so on. But here, 3D printing requires different thinking. So it's about leveraging geometric freedom, how we minimize the support and optimize for layered depositions. And 29% is about lack of confidence. So some might heard about the failures like this technology is not able to no, come up with a surface finish or a demanded finish cannot be attained. The material properties are not matching with the conventional methods. So these kind of things lacks confidence. So, but still, people have been working on this, and a lot of things are getting matured in this particular technology. So now it has come in par with other manufacturing technologies, and even it has replaced the conventional uh, manufacturing technologies also. So there are three pillars in design for additive manufacturing. So right, like from
He is currently
DFM, that is
working as
design
an
for manufacturing, to design for additive manufacturing. So DFM, that is design for manufacturing, is about it's a general term. It could be any manufacturing process. It could be CNC, or it could be machining process, or it could be for metal forming, forging, and so on. But DFAM, on the other hand, it's meant for 3D printing. So it's about optimizing layer deposition, the geometry, support structures, and material directionality, and so on. And it's also about different constraints, different possibilities, and different rules. So this basically addresses the limitations in the traditional manufacturing. So let's say a CNC cannot create internal cavities without drilling from multiple angles, which could cause a lot of time and cost. So this can be done at ease in additive manufacturing. Similarly, a mold requires very complex undercuts. So this can be dealt easily in additive manufacturing. And there are so many uh, positive or the advantages that we have in additive manufacturing, and also the capabilities of additive manufacturing. So if you want to build some internal geometries, let's say dies with internal cooling channels, so it's quite easy to do it in 3D printing. So you don't have to build in, you have to no need to do drilling or assembly. These kind of things have been completely eliminated. And if it is complex shapes like organic shapes or something, that it can be easily done in 3D printing. Like I said, it's about layer by layer deposition, right? So it makes the process ease. And if you want to do hollow structures with infill, basically for lightweighting, that can be done. That can be achieved in 3D printing. So what is the aim of DFAM? So this has been told by the pioneers of 3D printing technology or the additive manufacturing. So the synthesis of shapes, sizes, geometric mesostructures, compositions, and microstructures to the best utilized manufacturing process capability to achieve the desired performance and other life cycle objectives. So from this, what we can infer is like it's about shapes and sizes. So it's about every curve, every dimension, every angle that has been optimized for performance. It's not been, I mean, additive manufacturing is not constrained by tooling. It's designed for the actual physics. And next is about the geometric mesostructures. So it's about latticing and infill patterns. So you can make internal architectures, and it's been lightweight and also it's been strong. So where the optimized density distribution is there. So this is quite impossible in traditional manufacturing process, and it's only possible in additive
Have so
manufacturing.
many other immediate
And also it's about
applications where
material compositions and
communication has
microstructures,
become a
like which
protocol.
material, which alloy, which properties, then how should it be deposited to achieve no desired strength, ductility, or thermal properties, and so on. So here, the printing direction matters in 3D printing. So in what direction you print, and it's about the layer orientation, and also the microstructure here can be engineered. So it's unlike the conventional process, here it can be engineered. And then it's also about the manufacturing process capabilities. Like we need to understand what printer we are going to use for printing. So basically, we need to understand the resolution, support requirements, material compatibility, or it's about thermal gradients. So we need to design in a such a way that it can be printed on a chosen 3D printer. And also, it's about desired performance and life cycle objectives. Like, what does this part need to do? Like, what should be its strength, thermal conductivity, biocompatibility, cost or weight? So, DFM actually synthesizes all of this into one optimized designs. So that is the biggest potential of the additive manufacturing process. So, what are the drivers of additive manufacturing process? So, we have material efficiency. So, you can see that you can eliminate a lot of waste. So it's like direct reduction in the material cost and also the waste disposable cost. And next is the mass customization. So you can see the hearing aid as an example. So hearing aid, you know that it's been specific to the patient. So where it can be printed at ease. Conventionally, it takes time, a lot of time to get it done. But here you can do mass customization where you can print multiple hearing aids in one bill. So this helps to minimize the time and also the market differentiation across the technologies. And then third one is about the functional integration. So you can see the complexity and the internal passages or curves, the
Don't have that
integrated
much
features
time.
that has been
So
shown.
I have two back-to-back
So
sessions.
here, this
The
entire
first session
part,
I will
what
be
has been
discussing
shown,
about
can be printed,
a
can be
simple
integrated, and
example
it can be printed in a single
with
bill.
k nearest neighbors
And
algorithm.
there are
Then I
so
will
many
also take a
applications that
data
we
set,
can see
a
in
real-time
functional
data set,
integration. Like we
to
have heat
explain
exchangers,
multi-class classification.
fuel distribution systems, ventilation systems, and so on. And
Computer
flow optimization.
is going to
So this is
learn
about
some experience E.
the
For
optimizing
what?
the
It
fluid
will
and
gain
thermal flow. So how
experience
effectively it
with
can be done. That
respect to
passage,
a
how we can
specific
optimize it.
task T.
The internal
Now,
ribs,
when you have a
curves,
task
channels that has
T,
been designed for
it will learn
maximum heat
some
transfer or minimal pressure drops. So those kind of things can be optimized. And it's predominantly used in applications like
distance
heat sinks,
between
cooling ducts,
that new
say
data point
hydraulic
to
no
all other
manifolds,
data points,
and even
right?
for
For
heat
example, you
treaters for
see, I think
electronics
everybody
and
knows
so on.
about the Euclidean
And also
distance
we have
formula.
this tailored
Root of
porosities and
x2
properties.
minus x1
So
square plus y2 minus. Here,
here you can actually
x1,
control the
y1 are the
porosities.
coordinates
So
of
this helps to
one data
create
point,
lightweight structures,
which you want to check,
which
and the other
can
data
be
point
done
is
with specific
x2, y2.
stiffness,
Now you
damping,
calculate
and
the
acoustic
distance.
properties. And also we can have a control
Imagine
over
a scenario
the
like
grain
this.
boundaries. So it helps to influence the material strength,
Two blue
ductility,
color
or you can see
category B
the
are near
fatigue
to E.
resistance.
Three green
And
color
it
data
finds
points
its
are near to it.
applications in
So
graded materials
3
like
is the
where hard
majority.
surface for
Category
wear
A
tough
will be the
interior for
new
impact
data points
absorptions and so on.
category. Like this we will
And the
do.
last one is about,
Any doubts here?
uh, okay, so the part consolidation is about how
Now,
we minimize
the
number of
question
parts.
is,
Let's say we have
how do I select
a
the
part
K value?
which is shown here, which is
How
basically
do
a
I
duct.
select the K
So
value?
where it has got 5 to 8
We
parts.
can
So
select the
it
K
can be made as a
value.
single part,
We
a
can
single integrated part.
select
So
the
this
K
actually
value
eliminates the fastness. So and also the assembly and
randomly. There is
assembly time
no
and labors who
mathematical
are involved.
model
It
to
can be eliminated
define
completely.
the
So we can
K value.
um, make it
Okay.
as a single part,
So
and it can be
how do
printed at
we how do we select
lowest
them? Usually
assembly
what we do is,
cost,
in
lowest failure
general,
points, and it has
you
got
should
highest
not take
reliability, and I can
even
say
number as K.
shortest lead time
Sir,
also.
why I should not take even number? Very simple. In cricket,
So in
every time if there
continuation
is a
to the
ODI
discussion
series or
on
anything,
DFAM
usually
methodologies,
they
we
say
also
3 match
have
series, 5 match
topology
series.
optimization.
In test only, they will say
So this is
one
about
or two
topology
because test there is
optimization
every
of
possibility
hip
of bias
processes.
also. So
So
what
we
I am
can
saying
see
is
the optimized and
odd number is
unoptimized
only the
version of
tiebreakers. For
the hip
example, you take
process.
k
On the
equal to
left is
4.
the
2
unoptimized. On
points
the
are
right
near
side,
to
you have the
category A,
optimized.
2 points are near to
So
category
it's
B.
about removing
Then
the
where I will go to, where I will
material
categorize, which
which is subjected to less stress
suppose
or
if there are odd
lower
numbers,
stress
then
regions.
there is
The
always a
material has been
tiebreaker.
removed,
Is it clear?
and
In general,
this
K
is
is
done in a
not
way that
even.
it is not compromising the
Then
functionality of the part.
K should
So the objective
be
here is to
small
minimize
value,
its weight,
very small,
and
like
it's
1,
basically
2,
to
like that.
minimize the
Why?
compliance
Why?
or
Because
maximize its
if you take
stiffness.
1, it
So
leads
that is
to
the
more noise.
objective.
Why? Because
And then we have
everywhere, for
latticing.
example, you will get
So
everything you will get.
latticing,
Means
here
for
you
this
can see that
category
it's
also you will
been
get one
done
nearest neighbor.
on a
The
skull
other
implant.
category also
So
you will get nearest neighbor. One more category
where
is
you
there you will
have
get nearest neighbor.
different
Then how you will
unit
choose?
cells for doing the
So
latticing. So anyway, we'll
what
discuss
we
more
do in
about
research
latticing
work
in the
is
forthcoming slides.
we
So you can
take
see
different
you have a
values of
CT
K, analyze the
scan that has been
accuracy
done,
or
and
any
based
other
on that,
performance
a
metric,
3D model
and
has been
then
generated,
we choose
and
the best
it's
of
been
the
printed on which
values
this
by trial and
cranial
error
implant has been
basis.
placed that you
Is
could
it
see.
clear?
And next methodology is about generative
Is
design. So
it
generative
clear?
design is something that
Okay.
gives you
Now
multiple
let's see a
outcomes
typical case. Imagine you have
for
taken
same
K
input.
equal to 3.
So it's like
Imagine
the
you
outcomes
have
are
taken
based on
K
the
equal to 3.
manufacturing
Now I
methods, and
highlighted
it's
in the
about
PDF.
the
When you
objectives
take
what you have
K
defined,
equal to
whether
3,
you're trying to
one star
minimize
point is there, which is class
the
A.
weight, or
Two
you're
triangle
trying to
points are
maximize
there, which is class
stiffness,
B. Now our
And
machine learning
it's
algorithm
also
will
about the
say the
materials. So
new,
what
the yellow
material
question
and
mark data
manufacturing
point
methods, whether
belongs
you're going to
to
do it for
class
additive
B.
manufacturing or machining, or you're
But
going to do it for
what will happen
casting
if
and
I
so on.
say
So that
k
can be
equal to
defined.
7?
And you'll have multiple outcomes
Same
where you
data
can
point,
choose
k value
the best
differ.
outcome
Now you see,
based on
if
the
k is
user's
equal to
applications.
7,
And then part consolidation, I
3
think
data
already we have
points
discussed.
of
It's
triangle are
basically
coming,
reducing number
but
of parts,
4
and
star points are coming.
we have mass
So
customization.
there is every possibility based
So
on
where
the
we have
k,
this
your
hearing
category
aids, so which can
may
be customized
change.
according
So
to
that's
the
why
patient.
we go with trial
And
analysis
we have
and
this
select the best
multi-material
k value.
printing. So
But there is
you can
no
see that
formula
there are two
available
technologies
to
that are
select the
involved,
k
3D
value.
printing technologies that are involved, which is
Okay.
laser based
So
powder
how
bed
do we
fusion
select?
process. The other one
As I
is
said, there is no
the
predefined
direct energy
statistical
deposition
methods.
process, where they have used
So you will take random k.
laser based
You should not
direct
take a
energy
small
deposition
value
process, or we say it
because
as laser
decision will be
metal
unstable.
deposition
You should
process.
not take so much big values
So
also.
it's kind of a hybrid
And
process in
you
which this
go with
particular part has been
the
fabricated, which
minimum
is
k
the
value,
bimetallic
the
coupled
optimum k
chamfer.
value,
So this
which
comes
gives the
from NASA.
minimum
So
error rate.
you
Sir,
can
what is
see that
error?
it has
Error is
involved
nothing but how
two
much you are
different
deviating from the
materials with
actual
two
value.
different 3D
You
printing
have some
technologies.
data,
And next is
right?
about the
And you
multi-scale
know
printing.
the
So where
data point also. I'm
you
talking
can
about
see the
supervised learning.
osteoanchor implant.
Then you test
So
it,
which is
then check whether it is the
printed
actual
in a way that
value
you could see
is
at different
equal to the
scales, like
predicted value or not.
from
Okay.
the
Now
let's
let's
say
come
you can
and
see it
try to
at a
learn
different angle, like from
some practical
micro
concepts
to
here,
the meso level.
right?
So you can see
Now
the
I'm
resolution of
opening
the printing that has been done.
a program. I will explain
And the last
every line.
methodology is the design rules.
I will
So how do
explain
we
every line with a simple
no,
example. Now I am going to
design
take a
part
very
for
simple example.
additive manufacturing based on
Then
some
later we
rules?
will go
So
through
for
a complex
example,
example. Okay. So I
overhang
love to
angle that
explain
we need to
via coding.
consider
So
for
don't
the
worry
additive
about the
manufacturing
number of
process.
lines
So
at
where we
all,
have a critical
right? Let's go
angle
to
of
the
45
PDF
degree,
also.
so which is universal across
You
all
can
the
see
3D
here
printing technologies. So
we
whenever a
have
surface
a
is going
Python
to have less
library
than
called
45,
as
it requires a support
scientific
structure.
kit
If it is
learn
printed without
library.
support structure, it's
In
going to fail.
shortcut, it
And
is
likewise, we have some
SCIKIT
rules
scikit
for
learn
holes.
library.
So let's say you want to print a hole which is going to be greater than 6 mm.
What
So that requires
scikit
a
learn
support
library
structure. If
offers
it's going to be
is
less than 6, it
scikit
doesn't
learn
require support
library
structure.
has
And
so
instead
many
of going for a
models
hole, you
of
can a
machine
cylindrical hole. You
learning
can just go with other
developed
profiles. For
inside it.
example, you could go with
So
teardrop kind of
we
holes.
can make use of
So these
scientific
kind
kit
of
learn library
fundamental rules that
and
we
we
need to
can
follow
actually
to design the part
uh,
for additive
learn,
manufacturing.
or we can
Now we'll
actually
start
work
off the
with
discussion
several
related to lattice structures.
machine learning models.
So first we will
So,
try to
sir, how
understand what
to
is
install
lattice
this,
structure.
where it is available?
So
It is very
lattice
simple.
structures in
You
3D
have to
printing are
just
nothing
type
but the
PIP
internal
install
architectures that is made of repeating, or you can say
scientific
it
kit
as
learn.
mathematically defined unit cells. So they are designed to tune
Scikit
mechanical, thermal, even
learn.
biological or
This
other
is the
functional
right
performance
now I have
using
already installed
minimal
it.
material.
So it will say
So it's
requirement
about a
already
network of
satisfied. But in case if
interconnected
you want to install,
struts or
this is the way
surfaces
you have to
that
install.
actually creates
PIP
a porous
install.
structure. So by means of that,
Now,
we are doing
every
lightweighting here.
line I will
So
explain.
and it
If you
also
are
it's
not
done
understanding,
with
please
some
let me know.
controllable
A
stiffness,
simple
high
example
energy
I am taking.
deposition, and also
Okay.
multifunctionality.
The first one
That
in
makes it very
Python,
hard
I
or
took a
impossible
list.
to be done
Line
using
number 3.
the
I
conventional
am taking some
manufacturing
different
methods. Like you could see in
combinations.
this images that
The weather
you
forecast,
can just think
sunny,
about traditional manufacturing
overcast,
process.
rainy.
So whether
Different
those
values
processes
are
can
given. A
actually make
simple
this products.
list. You can
It's
see
highly difficult, but
line number
it is
3 is
quite
a
easy to do
simple
it in
list.
3D printing.
Then line number
And these
5.
are the
I am
unit cells
taking
that are
another
used
list called as
in
temperature
the lattice structures, where
or
we have strut-based
mild,
unit cells.
cool. This is the
Like let's
combination.
say you have body
So
center
you have
cubic,
3
diamond,
unique values in
and you
weather:
have
sunny,
yeah.
overcast,
So these
rainy.
are very simple,
In
and it's
temperature,
actually
you
predictable,
again
and
have
also it's
3
isotropic,
different
where it
values, that is
exhibits
hot, mild,
same
and
properties
cool.
in this in all
These are 2
directions.
different lists.
And we have
Now, I am taking one more
Kelvin
list.
cells, and then
Consider this is the
rhombic
target variable.
rohedron, and then
Ideally,
we have
weather
truncated
is one
tubes.
feature,
So these are actually used
temperature
for
is one feature.
very
Now you
complex,
see
and
the first
also for
value in weather,
better isotrophy or high
sunny,
stiffness.
first value in
So
temperature,
when we have to go for this
outside it is very
strut-based unit
hot and
cells,
sunny,
so
play,
we will be
don't,
using it
that
for
means do
structural
not play.
applications
So in the
where
data
stiffness is
itself,
very critical,
play
and
is
also
the
for
target
straightforward
variable.
manufacturing,
So this
mostly
is very much
strut-based
applicable
units still
to
are preferred.
supervised
And
learning.
then we have this flat
Is it clear?
sheet-based
I
unit
have
cells.
taken
So
three,
they
weather,
are made of flat
temperature
surfaces,
as
like folded origami,
uh,
and
input
it's like
variables,
lower complexity
independent
than the
variables,
strut-based.
and then I am
And we
taking
have this
one more,
triangular,
that is target
re-entrant,
variable.
square, and then
Is
rotated,
it clear?
square, hexagonal, and so on. So we would be using these kind of unit cells
Is it
where
clear?
it demands for high strength to weight and moderate complexity.
Yes, yes,
So these are very
sir.
easy to
Yes.
generate.
Yeah.
And the special
Now,
property about this is like
when you install
the
SK learn,
re-entrant.
you
So
can see
it's about
here,
negative
when
Poisson
I
ratio. So it
tried
expands
installing, it's a
laterally when
requirement satisfied because
and
I
it's
have
been
already
counterintuitive, but
installed it.
it is useful
Now,
for
sir, where
damping
do I get
purpose.
this?
And then we
Let
have
me
this
open the,
TPMS,
say
that
as
is
a faculty,
triply periodic
when you
minimal
are
surfaces.
learning something, we
So
should
where
learn
we
in a
have
way where
this
we will
TPMS sheet, and then we
explain
have
the
skeleton
students in the
based.
better
So in sheet we
manner
have
where they will
gyroid,
understand.
diamond, and
Now,
split P,
I am still using
linoid,
a old version because
stivots.
I don't want to
So
update
these are
and
mathematical
get
surfaces
into
with
trouble.
zero
So
mean
this is my
curvatures, and it's
Python
been
home.
optimized for
But for
surface area.
you, maybe you
So
will
they've
install in a
been
different directory. Then
used
you
for
will go to Python
bioscaffolds,
home.
and the
Inside Python
maximum
home,
areas for no
there is
cell
a
attachments.
library
It's been continuous,
directory.
and no
Inside
sharp
this,
stress
there is
concentrations are there in
something
this
called
kind of
as site
itself.
packages.
And in TPMS
Every
skeletal based,
library
that
which
is,
is installed
it's
in
actually a
Python
sheet
will go
based
to
variant
this particular
where you
directory.
can see it's of
So
same geometries and
here
different connectivities. Been
for
robust,
scikit-learn,
and it
when
has
you
better
install,
mechanical
it will
performance,
come as a
maintaining the
subdirectory
biological benefits. That's why it's
sklearn.
been used across many medical
So
implants,
this is the place
bioscaffolds,
where my
and also in
learn
fluid dynamics like heat
sklearn
exchangers
is
and
installed.
microfluidics.
Sir, how I know? You can clearly see scikit-learn is installed here. That's exactly what I have
So
opened
now we will
in
discuss
another
about the
command prompt.
steps that are
Now,
involved
if
in
you just list there are
the
so many things which will
lattice
come.
structures. So how do we
Okay, I will
create lattice
few things I
structures in
will also
softwares?
explain.
So first we need to
Few
define the
things I will
design
also
intent. It's like
explain.
establishing purpose,
Okay,
the target properties that are required,
I
and the
cannot explain the
constraints. Like
entire
you need to ask questions like
library, but
strength,
one
thermal,
or two I
weight,
will explain.
biocompatibility,
Now,
what is the volume
let
limit,
us
what
try
is
to
the
understand
cost target, and so on.
line number
And the
9.
next step is to
Let
import
us try to
and
understand
prepare the CAD
line
model.
number
So it's
9.
like
From
you need to repair the CAD
sklearn
file if in
preprocessing,
case it has got some
import
errors.
label
And
encoder.
also
What
you
is
need to
this?
identify the solid regions
sklearn is the package.
for
Then
if
what
there
is
is any
dot
overlaps, any holes
is?
or
If
gaps
there
that you need
is
to
sub
clean up
package,
before
let's
latticing.
go and see.
And then the third step is about defining the lattice design space. Like it's defining the core or surface zone. And also you have to define the
Now you
exclusion
can
regions.
see
So where you
there is
don't
a
want
sub package called
things to
preprocessing.
be latticed. So those
Inside
exclusion
this,
regions you need to
we
define
are
it. Like
trying to
say
import
you
label
have a
encoder.
fastness or
We are
something
trying to
where you
import
want to eliminate.
label encoder.
I mean, you
Now
want
I
to
will ask
uh,
the
say that you
participants
don't want a lattice
in
structure
line
there, so you
number
have to
11.
inform the software that
I
it's going to be the
highlighted
exclusion
something.
region. And the
Label
fourth step is
encoder,
important step. Like
open
you need to
parenthesis,
choose
close
the right
parenthesis,
lattice
dot.
type depending upon the
What is
applications.
this label
So
encoder
whether you have to go
according to
for
you
TPMS or strut based or
with a
biomedic
programming
lattices,
perspective?
those kind of things. So already we have discussed about different lattice structures and its potential advantages. So based on that, we need to choose the right for the application.
It is
And
a
then
function.
step 5 is about once you have chosen the
There
lattice
is a function.
structures, the next step we need to define lattice parameters. So it's about setting the unit size. So what should be the size of the lattice
Right,
structure, and what should
Anybody
be
specifically
the
else?
strut
convert to
thickness,
numerical values,
and what should
No,
be
no,
the
the scaling
density.
works only on
So the
numerical
unit
no.
values.
size,
No,
if you're
I
going
didn't
for a
mean the
fine
label encoder
value,
does.
it's going to
I
take
just told
a lot of time to
when it is
print.
written like this
And
in a
if it's going to be
program,
coarse,
what exactly is
it's
this?
going to be
Somebody
very
said it is a
fast, but
function.
again, it will be very coarse.
Yes, it is a
That's
And
function.
what I am expecting. Not what label
it again,
encoder
the
does.
parameters defines the
Okay,
properties of
this is not a
It's a
function.
method.
the
This is
print.
not a
For example, if you
function,
take
it is
stud
not a method.
diameter, so it actually controls
This is
the
the
stiffness
place
and weight.
where
So
I'm
and
sorry
also
to say,
that
I'm not pointing
you
to
can
this
vary the density,
particular
like I said.
group of
If let's
faculty.
say you're going
In
to go
general,
in for a value of
faculty
5%,
is
it's going to be
not
super
getting
light, and if you're
clarity
going for
between a
50%, it's
method
going to
and a
be a strong
class. Why?
part.
Because
And then
of
now we
late,
have to define the
I'm very sorry, I'm very frankly
lattice
telling, I'm
structure.
not
So we
pointing
need
to
to
anybody. We don't
implement a
write any
uniform or
coding.
graded lattice
We
structure.
only
So
tell
uniform in the
theory,
sense it's going to be
right? That's why
same unit cell
this
across,
label
same
encoder
unit
is
cell
not a
size across the
function.
part.
It is not
If it
even
is
a
going to be
method.
graded,
It
you
is
keep
basically
varying
a
it
class.
hierarchically
There is a difference between a class and a
across the
function.
part. So
There
that
is a
if
difference
it is going
between
to be
a
uniform,
class
we're
and a
going to
method.
use same parameters
Fit
everywhere, and
underscore
it's
transform
easy
is a
to predict the
method,
properties. And
but
but
label
whereas in
encoder is a
gradient,
class.
no, the
But
density actually varies by
how can
region,
you say it is a
so
class?
it requires
So what we have to
optimization, and
do?
also it's a bit
We should
complex to
do
do some
Python
predictions.
postmortem, not the
So
real Python snake
whenever
postmortem.
we're going for higher
Whereas we
density, there
should
could be a
do
lot of
the
stress
postmortem
concentration
in
areas.
this way.
So lower
Where
stress
is it
regions will get
available?
sparse lattice.
Inside SQL and
And
pre-processing.
step 7 is
Now, when I
something that is
say it is
optional. Like
available,
if you want to
so I
do
have to open
FEA based
and
mapping,
see.
so like
But if I
evaluating stress
open and
strains
see
and
here,
generating the density
I don't
fields,
understand
like
where
running
exactly it is there.
FEA on structure
There are
with
so
lattice,
many
so those kind of things.
Python
So
files
this is
here.
like doing
Any
simulation. So it
time,
will tell you
remember,
where
you want to
density should increase or
understand any
decrease.
library,
Even you can
inside that
integrate with
library
the topology
and
optimization.
open
So
the
once the part is
init
optimized
file, which is
using
the
topology
beginning
optimization,
of
that you can
any
subject to
package's execution.
the latticing,
So
so
I
that
open the init file.
it helps to
Now
reduce
inside
weight
the
further,
file, you will be able to
and so on.
understand
And
what you are
step 8
searching.
is about
So
trimming and
what I
blending the
am
lattice.
searching,
So it's
label
like
encoder. Correct?
conforming to
No.
the boundaries
What I
and
am
also the
searching,
smooth joints.
I
So
want to search
the
what is
lattice
label
edges that can
encoder
be
does,
racked,
or
so where they intersect
what exactly
the
is
outer
label
surface,
encoder, right?
and some trimming and
So
blending needs to
I
be done
open
to
the init
create
file,
the smooth
then I have to
transitions,
search where
so that
exactly it
there
is
is
there.
no sharp discontinuity.
See
So
here,
this could
in line number 32,
decide the part quality and helps
import
to
label encoder.
reduce the stress
From where?
concentrations.
From dot
And step 9 is about
underscore
the
label. That
manufacturability
means
check. So where you
label
have to
encoder
verify
is
the stud
available
size,
inside
and you need
another
to
file.
watch out for the overhang angles. So
Dot means
angle
current
is going to be less than
directory.
45,
And
requires
I think in
support
you know
structure. And
about
again,
under
it
methods,
should not
single underscore, double
become
underscore,
difficult for us
as
to
we are
remove the
not
support
teaching
structure in latticing.
Python here, so
And
I'm
again,
not
we have to make sure
stressing
that
too much.
whatever lattice
But
that we
we
create
have to
should
search
not create
whether
trap
underscore
powders
label.py is
in
available
case
or
if we're
not.
going in for
Yes, it is available.
laser-based
What
powder
is
bed
dot
fusion
here?
process, or if we are going
Dot
in
means current
for
directory. Yes, it is there.
resin-based,
Now we
there
have to
again, there
open
are
that.
chances that resin might be trapped. And
Python
so these
hides
can
so many
be
things. So that's why
resolved
many
by
people say Python is easy, sir.
looking at the
Python is
parameters.
not easy, or C language is
So
not
how do we optimize
difficult.
the
You
parameters
should
for that?
open and see what exactly
And
is
then
there. Now
the
here,
steps.
there are so many things.
Next
But
step is
what
about
we
the
are
process
looking for,
simulation. So we
we are
have
looking
to
for
simulate the
label
part for distortion
encoder.
and residual
What
stresses,
is label
so that
encoder?
it helps to predict
Clearly it is
warping
written.
or residual
It is a
stresses,
class.
and sometimes it
So
helps
just
to
because
validate
there
the
are
mechanical or
parentheses,
the material
you should
properties.
not think it is a function or a method,
And last step
right?
is once all
Because
this done,
class
and if it
will
is
have
thoroughly checked, we
constructors.
can export it for
Constructor can be called as a method
AM,
only,
that is
right?
additive
So
manufacturing
label
process. You can
encoder is a
export it as
class.
STL or TMF
Label
files
encoder is a
with the right
class.
resolution and mesh quality. And at last, we can go in for preparing data, that is
Okay.
slicing the part,
Now,
generating
when we
supports,
tell
and then creating
this is a
the
class,
path
what
for
it does.
printing. And finally, you can just
Now
print
let
it.
us see what it does. Label encoding is one pre-processing technique
So these are
where
some case
for
studies
categorical
in the
value,
lattice
you will
structures.
get
So what
some
you're seeing is an
encoded
hip implant.
numerical
So
values.
where you can see that
Because this
there are
class is not
different
about the entire pre-processing.
lattice infills
So
that has been
simply I am
done here.
explaining.
So here
For
we have
example,
this double pyramid, and
you
then we have
have
face diagonals and octahedral.
sunny,
So here the
overcast, and
porosity
rainy.
range is around 50 to 83%
Alphabetical order
in case
you have
of
to do.
3D lattice
What
infill,
label
and for
encoder
double
does is
pyramid and face
it will
diagonals we have
it will
51 to
take
86%,
in
and
alphabetical order.
octahedral is from 51
In
to
alphabetical
87%.
order, what
So
happens?
meaning that we'll have relative
Which
density of
alphabet will come?
17 to
M, N,
50 in
O,
case of
P, Q, R,
3D
S.
lattice infill, and
So M,
for
N,
double
O,
pyramid and
O,
face
overcast
diagonals
will
we
come
will
first.
have 14
Then
to
overcast
49% relative
will be
density,
getting a label
and
0.
octahedral lattice will
M, N,
have
O, P,
around
Q,
13 to
R. R will
49%
come
of
next.
relative density. It's
Rainy,
actually
R will be
a
1.
machine learning model that has
Sunny
been
comes
developed
last.
in this work to
Sunny
pretty
will be 2.
the
So what is
outcomes.
label encoding?
So the second work
Label
is about
encoding is converting the
lattice, which
categorical value to
involves
the numerical value. Then you will get a
gyroids,
doubt.
Schwartz diamonds,
Why
and
should I convert?
Roni. So it's
Because
actually done for
many
high
machine
mechanical
learning
strength, and
algorithms expect the data
it has to
in numerical
match with
values.
the bone
But you have
performance.
categorical
So
data. What do?
here they
You
have done the
pre-process it.
functional
Label
graded latticing
encoder, one
zones.
hot encoding. There
So
are
the
some
lattice were placed
many
only in
techniques.
regions of
So
lower
here
stress to
I am
balance the
using
strength and also the material
label
savings.
encoder.
So this
I am
functional
using label
gradation
encoder.
actually
So let's go to the
improved the
code now.
mechanical behavior when compared
So
with
if you
the
want to learn more
uniform
about it,
lattices.
I showed you how to go inside and see
And
which is the
this
class, which
shows
is the
that the
method, what
Schwartz
are the
diamond lattice that
arguments
has been
that
used,
will
that
go,
is
what are the default
the best
values,
among the three
everything you
lattices
can
that has
go
been
inside
used
the
in the work.
predefined library files and you can see.
And likewise, you
Now,
have this prosthetic leg,
inside
so where
label
they have
encoder,
imposed
there
lattice
is a
structures
method
on
called as
a particular component of
fit transform.
uh, the
What it will do,
prosthetic leg,
it will fit
and they have
and
subjected it to
transform
body-centered
the
lattice
categorical
structures
data
with
into
controlled relative densities
equivalent
of 30
numerical
and 50%.
values.
And
Is it
also,
clear? Line number 11, is it clear?
you can see that this work actually demonstrates the lattice-based spring behavior, where we can actually tune the
Let's continue.
outcomes, that is
Similarly,
stiffness and
now
energy
what
absorption.
will be the outcome? Encoded weather. Weather is
So the next work is about
sunny,
the
overcast, and rainy.
osseointegration.
Then you
So
will get combinations of 0,
here you
1,
can
2.
see that we have
Similarly,
dental crown
what
over an
I am
implant,
doing is
showing the
for
bone
temperature
implant
also
interface.
I am using
So
the
the
label
traditional,
encoder. Then here also for temperature I will
titanium
get some
implants rely
values.
on mechanical
Then
interlocking.
whether
So the
to
bone
play or
cells
not,
will slowly
that
grow around
also
the
I am
implants. It
using the
takes
same
like
encoder.
3 to 6 months
So
for
finally what I did is
stable
I
osseointegration
have
to happen.
taken the
And also you
category
can
values
see
and
the
change
cross
it to numerical
sections
value.
of
Now,
the implant bone
this is a small example,
integration,
right?
and you can see that you
Here,
have a fixture
weather is a list,
where it is
temperature is
surgically
a list.
placed in the
They
jawbone,
are
and then we have
completely two
abutment.
different lists. It is not a
So
data
connects
set
the
here.
fixture to the crown, and
So
you
what I
can
am
see
going
the
to do is
visible tooth there.
I am bringing the
And we have
combination
the bone integrations, like
SUNNY
bone growing onto
sunny
the surface, which
and
is
HOT hot together.
very critical for the
Second
integration to happen.
instance, sunny
And on
and
the right hand
hot
side, you can
together
see
as a
that there are
tuple.
5
Then
different screw
overcast
designs.
and
We
hot,
the different
rainy
lattice patterns have
and
been used, like
mild.
stud-based and
I want to
TPMS has
pack
been
them in a
used,
tuple.
where the
How I am
porosity
going to
levels have
pack?
been varied, and also we
Here
have
in line
thread
number
geometry
23.
optimization has also been done.
Set IP.
And there are
Zip
some
will
profiles where
pack
it's been
the
parallel and it's been
values
too
into a
tapered.
tuple.
So those kind of
So what this will
studies
do,
have been done, and this
it
is
will take the
done.
first
I
value
guess it
from
is
the
in
encoded weather,
NTOP software.
first value from the encoded temperature, it will pack
And
as
this is
a
about
tuple.
the
All the tuples I am
mandibular
converting into a
processes,
list.
and
Finally,
you can see
I will
that
show you in the PDF itself what
uh,
outcome will come.
it's about the
Clearly,
latest
you can
processes, I
see
mean lattice processes that has been
sunny
used,
got
that has
value
been
2.
used to
Again
simulate the
sunny
missing
2.
mandibular segment,
Overcast
where
0.
it has been assembled
Rainy
into
1.
no
This is
patient-specific jaw
encoded
model.
weather.
And you can also see that
Similarly,
there has
encoded
been a
temperature.
mandibular before and after
After
coating
that,
or installation.
what I am
This actually
doing, I
highlights
am combining the
how the lattice
features.
implant is
Clearly,
fixed
you
with
see,
screws,
first
and it's been
value in
integrated
encoded
into a
weather is
surgical
2.
model
First
before
value
actually
is encoded temperature
going into
is
the
1.
patient.
Now you see
And
2
you
and
can
1
see
is one
different
combination.
lattice patterns that has been used.
Okay. Based
So
on the
it's about
combination
the
2 and
porosity.
1,
So lower
if the
porosity
combination is 2 and 1,
actually shows
basically
gradient
sunny
lattices, where its
and 1
pore
is
size
hot.
and density changes across the
Play is
implant, which
0. Do
is
not
tailored to
play.
stiffness and also promote
Now you see the
bone
next
growth.
combination. Third
So,
combination,
and you
0
can
and
see the
1.
actual
What is 0? Overcast.
uh,
It is overcast and it is
latticing that has
hot.
been done.
Yes, you can play.
So
So basically
there you
what we
can see
got
the
is,
3D printed
we got
titanium mandibular
the
reconstruction plates with
input
the integrated
features
lattice
and the
windows.
outcome variable.
So which has been mounted on
This
the
is
jaw
about
models with screws. These are
data.
actually
Now what
titanium
we have to do?
implants, which is done for the
We need
mandibular
to implement
reconstructions.
k nearest
So
neighbors binary classification.
actually, these implants are too
So
stiff. They
let us see
exhibited
line number
modulus value
28.
of 110
Let us see
GP. So
line
bone
number
normally it will be from
28.
3 to 9 GP.
Now
So
in line number
it's
28,
too
we have
stiff
from a
that
scalar
this latticing helps to relax
dot
those stiffness so that it won't
from
take too much of load.
scalar dot neighbors import K
So
neighbors
this is about
classifier.
the
Now
acetibular
again,
hip
what we have to
cups.
do? If
So
you really want to know,
where you have this
right, you have to go to the site packages. Inside
femoral
SK11,
stem
there is
and head
neighbors.
that has been articulating against
Yes, it is there.
plastic
It comes with
liner
practice.
that snaps into
Again,
the
list the values.
acepular cups
I
fixed in
don't
the
know where
pelvis,
it is written. What
and
I have to
you can
do?
see the
Simply go to the init.
lattice
Init file.
structure design actually matters the most
I'm
here.
going to the init
Like I
file.
said,
Now
there
you
are two
see
sites for
where it is available.
the
It is available
acepular
here.
implant. So
In
you
line
can see
number
that
12, from
the real
dot
cup with
means
a rough
current
side, which
directory,
is highly porous,
underscore
which
classification.
involves the lattice
That means
surface.
you have to go
This helps to grip
see
the bone
whether
by press
underscore
fit, and it
classification is
actually
there or
supports
not. Yes,
the
it is there.
integration.
Go here.
And the other side, you could see that it's been
Now
machined
you
so
have to
smooth. It
see,
has got a very
yes,
smooth
there is
surfaces,
a class
and you
called
have
as
some screw
K
holes.
neighbors
So this
classifier. So
liner
this is
snaps
also
into
not a
this
method.
smooth
Just
bore,
because there is parenthesis, you should
and
not get
and the
confused
lattice
and
actually
confuse the
is like
students.
for
Right?
for the
Now,
bone contacting side. So combining this
what it will
biological
do, as I
fixation
said,
with
you see here,
the joint
default
articulation,
K
the
value is 5.
implant
If you want to
has
change, you
been
can also
placed on the
change.
patient.
Okay. It will calculate the
Next is
distance.
about the
Everything
spinal
is written. There
implant.
are so
So
many concepts here. You
here,
can also go
this work has
and
been
you can
done from
see.
RMIT,
Here you see
Australia.
the how the distance metric is
So
happening, how pairwise distance is
it's about
calculated. Everything is written here.
uh,
Okay.
where the surgeons design the customized titanium implant. So this is done using
Let's
CT
continue.
scans and 3D
I hope I
printing.
am visible to you. There
And
is
you
some
have
power
this
problem here.
matched.
Anyways, now let's go
Uh,
to the code.
it's okay. So it's a it's
You see
actually
how
a lattice
simple it is.
structure
You are defining the
where it has
model, my
been
model,
produced
or
in
x
single
equal to
shot,
y equal to
like you
my
could see
model
on the
equal
machine.
to
So
k neighbors. You are
this
just
is
defining the class.
from Entope,
You
I
are
guess. Yeah.
actually
So this is designed in Entope, and
instantiating.
it's
You are
been
actually calling the class. That means you
manufactured
are creating
using
an object of that class.
laser-based powder bed fusion
The moment
process.
you
So
call the
this is
class itself,
a 3D
basically
printing
an
gate that
object will
is
be
used
created.
as
Okay. Now,
no,
with that
a spinal
object,
implant.
here you are saying n
So
underscore
next
neighbors
is
equal to 3.
topology
You
optimization.
don't send here, you don't set
So
any
topology
argument here.
optimization,
By
like I said,
default,
it's about
instead of 3, 5 will
uh,
go. But here I am
optimizing the material
exclusively
layout
mentioning
within the
3.
design
So
space
my
when it's
neighbors
been
will be 3.
subjected to, say,
Then
some loads or boundary conditions or
see here,
constraints.
my
So
model
here the
dot
objective
fit,
is to maximize the
the
structural
features.
performance.
What
So
are
it's like
features? It
removing
is coming from
unwanted
line
or
number
unnecessary
23.
material
What is line
then
number
and there.
23? The
So it's about
combination
retaining
of
material which is
weather
having
and
or
temperature
experiencing higher
values are
stress.
my features. So I
And
am
there are
sending
different
the
methods in
features, and then I am
topology
also
optimization.
sending
You
the
have
encoded label
SIMP,
play.
level
What is
set, and
encoded
you have
label play?
BISO
That
and
either
heuristic
play or
algorithm
not,
based
0 or 1.
methods.
Now
So
here
predominantly,
learning
a
happens.
SIMP is what
Here
is used
line number
across different
33,
industries
learning
and
happens.
academias.
Now
And
once
now
learning
people
happens,
started
I need
focusing
to
on
predict
level
the
set. So
outcome.
level set with
I need
implicit
to
modeling is the
predict the
core
outcome.
research
So
area
what
that
I
is
am sending
happening in
here, you
topology
see,
optimization.
my model
So
dot
people are
predict.
doing
Here
more work
predict
on
is a
that,
method.
and extensive work has been done on
Fit
SIMP.
is a method.
And also
Fit
some
is a
works have
method
been
which can be
done
called
in
from the object
BISO,
of class
that is
K
bidirectional
neighbors classifier.
evolutionary structural
Predict is
optimization.
also a method which can be
So
called
there are
from the
different
object
constraints that
of
are
class
pertaining
K
to the additive
neighbors
manufacturing
classifier.
process. Like you have
So
overhang
here what is
constraints. So
happening?
it's like
I am sending
designing
some
part to
different values of
basically avoid the overhang
features.
faces.
For
So
example,
you can
0,
see the
what is
conventional
0, 2 here? 0 is
optimization that has been
overcast.
done. So where you have overhang
Sorry,
regions which require support structures. So
M
this
and
is like
OP, yeah, M and O.
optimizing a
Correct.
part
Overcast
so that it
and
doesn't
cool.
have overhang faces. So overhang
Cool come
faces,
first.
what I mean here is the
Hot comes
faces that are
next.
less than 45 degrees. So
Mild
how do we
comes
do that?
2. That means
So we
it
need
is
to basically
cool
identify the
and
face, and
mild.
then we need to
Whether
remove
I can
material
play
in
or
those
not, we
regions
will see
and
in the
make sure
outcome.
that uh,
So 3
we
different
have
combinations I
surfaces
am
only
sending.
greater
You
than
can see the
45 degrees.
predicted output
And
also.
not 45, you can also do it across different
For
angles.
example,
So
in the
that is the
PDF,
purpose of overhang
this
constraints,
is
basically to
the
eliminate the
execution.
support structures.
So it
And
says
next
in the first
constraint is the minimum feature
feature
size
which you are
constraint. So
sending as
every additive
0,
manufacturing
2, it
process
says
has
yes, you
its
can
own
play.
resolution,
That
like
is also
minimum
true.
features that could be
Right?
printed. So
Now,
for
how
example,
to
if you
know
take
whether the predicted outcome is
laser-based
correct
powder
or
bed
not?
fusion process, it's
For
like
that, we can have
150 to 200
classification
microns.
report.
So if you try
For that,
to
we can have a
come up with a
classification
feature which is
report,
going
which
to be
I will
less
tell
than
you.
200
Let
microns,
me give
then
a
it becomes
small
complex to
gap
print.
here.
So how do we control that?
Again,
So for
two
which we
minutes
have to
break
go in for this particular
so that you will
constraint, meaning of
digest
feature
what I
constraint.
said and
And
you
then
will
we
ask
have
me if you have
thermal
any doubts.
distortion and
So let me
residual stress
execute
distortions. So
the
this is like
program
to
and
control
show
the
you
shape distortions and the residual stress that is caused by
in
the
the live
thermal
what is the
gradients
outcome.
during no printing. So how do we control the displacements? So we need to basically do a thermomechanical simulation, try to find the distortion. The distortion here is nothing but the predicted displacement. So we need to fix the predicted displacement within which we need to design the path. So the places where we are getting more than the predicted displacement, so we will try to redesign it in a way that it's not exceeding uh, the displacement what we have chose for the
Now you can see the
optimization.
outcome also, right?
And this also helps to prevent recoater collision. So this has been specific to laser-based powder bed
Yeah.
fusion
Any
process.
doubts here?
So
You please ask me
recoater
in case
collision is
if you have
something
any
that
doubt.
should not happen while printing. This could
At this point
lead to
of time, if you
failure.
have any doubt,
So we need
you
to
can ask me.
basically consider this while doing the design part. So now here you can see that the conventional and I mean the part which is optimized conventionally and the part which is optimized with distortion constraint. So the conventional design, there are some potential areas where recoater collision can happen. So we are taking into that consideration and then we are designing it in a way that we don't encounter recoater collision and also it's within the
I
prescribed
stopped my session
distortion
here. Now
or
the 15
displacement.
minutes, it is a question and
And the
answers,
next
and then
constraint is about
we'll
enclosed
take a
void
5 minutes
and
break because it is
connectivity.
a back-to-back 3-hour
So,
session. So I
so when
also
we are dealing
understand
with latticing or any
the
or
difficulty in online.
the
So
parts like
I
what it is
stop here.
shown
If
here,
you have any
so there
doubts,
are
I
chances
will
that
clarify the doubts in this session.
the material may
Then
trapped
we will
in
continue with
the
the
cavities.
other topic
Like you
with
could see, we have
multi-class classification and
some
multi-label
cavity here.
classification by using
So there
KNN
are chances that the
classifier.
powder or the
So
resins
if you
may
have any doubts
get
or
trapped
if you want to
inside,
give any
which
valuable
becomes very
feedback, you can
difficult
also
to
give me so that
get
I
out
can
of it. So we need to design
revamp the
the
way I
part
am
in a way
explaining. If
that
it is
it should
okay, it
have
is
some
fine.
passage to
If you
vent it
want a
out.
different kind of
So how
explanation,
it
I
can
have
be
to
done.
adapt to
So this
it
is also one
in the next
constraint
session.
that we need to
Yeah, up to the organizers
impose
now.
so that the part
I
can
am
be
done with
designed
my
in a
first
way to
session.
vent
Any
out
question and
the
answers you have, you can
material
please
out.
ask.
And the last constraint is about hybrid manufacturing constraints. So where you have hybridization between um, additive manufacturing and about milling. So how do we optimize it? How do you optimize a part for hybrid process? That is what has been shown. So you can see the conventional T was about the conventional part, and AM is the part that has been optimized for additive manufacturing. And HASM is nothing but hybrid additive subtractive manufacturing. So that is the outcome that has been done for the hybrid additive subtractive manufacturing process. So here for subtractive, it's about the let's say the tool accessibility. So you define the tool size. So you know whether the tool is able to access in that area. There are chances that tool can hit and break. So based on that, we can do this kind of optimization. And these are the steps that are involved in the topology optimization. So first you need to define the design objectives, like whether you want to maximize stiffness or minimize compliance, plane energy, and so on. And you have to import the geometry, and then you have to define design space and non-design space. So design space is the space where you want to do the optimization. That is the material to be removed or the material changes to happen. And there are regions that you need to basically say it as non-design space where the design changes should not happen. So for example, you have a hole or the place where you apply the constraints or forces and so on. So those spaces are considered to be non-design space. Those are functional spaces. So we need to basically preserve those phases. And then assign material properties is like what material we are using for the part. So that we need to define. And then applying loads and boundary conditions like how much load that we are applying, whether it could be a force, pressure, it could be or displacement-based constraints. It could be fixed constraints and so on. And then defining the optimization constraints, like whether you are one for overhang constraint or volume fraction constraint. We have discussed so many constraints, right? So you can go with any of those constraints, or you can go with some combined constraints also if possible, like volume fraction with overhang constraints and so on. And then meshing. So meshing is very important. Like how do you mesh the part for the static structural analysis to be performed? So in that, we would be knowing the regions where it has been subjected to lower stress and the region has been subject to higher stress. We try to calculate the sensitivity, and based on the sensitivity, we will try to remove the material and finally come up with the optimized results. And that optimized results, again, we need to validate it. So we cannot just like that use it for the final application. So again, it has to be checked with the static structural analysis to make sure that it's within the stress limits. And finally, we'll have to export it for the actual manufacturing. So these are some test cases. I'll quickly run through the cases as I'm running short of time. So this one is about the uh, the hip processes, like where you have so where you have this solid implant, so which has been optimized. So around 30% weight reduction has been achieved, and where deformation is around 0.51%. And this is about the mallet splint, so where the weight reduction of 59% was achieved. I mean, 43%, right? I'm sorry, 43% was achieved. And this is about the cast and braces. So it's done on a 2D manifold surface. It's not basically a 3D thing. It's been done on a manifold surface. So that is human body surfaces, and then it's been done. And this is about the lower limb processes. So where 30 to 40% reduction was achieved. And this one, you can see this center portion is what they've taken it for optimization. So where they were able to get 45% of weight reduction. And this is about the this is the region connecting rod. So that connecting rod, they have taken it for optimization, which is made of titanium alloy, and 62% weight reduction was achieved. So likewise, we have other test cases. So this one is about 5 different designs. Like you have different weight reductions like 10, 15, 21, 75, and 18%. And this also you could see that we have weight reduction of 30 to 40%. Okay, I think I'll stop here because I have few more slides, but it takes a lot of time to finish. If in case you have any queries, you may shoot up.
Thank you, sir. This is very nice presentation. I think we have a few questions from participants.
Yes.
Uh, see, okay. This is the question from Ramkrishna. How to tackle porosity morphology in metal printing?
Okay, so it's about printing trial and error. Thing like whatever no parameters that you have, you need to print it like trial and error, and you have to get it done. So some test prints you need to do it, and then is what you have to get it right.
Okay. And another one question from Nidikonda Gopi Krishna. He is asking the same porosity problem, but he is asking how to overcome the porosity problems.
Okay, so it's like uh, working on the process parameters. Like you have, let's say, I'm from a laser-based powder bed fusion process, so I would suggest we need to optimize the parameters like, let's say, laser power or scan speed, hatch spacing, and so on. So we need to play around it to get it done.
Ah.
Then again, you have to do some test prints. So without that, we cannot say, like, there are some simulation softwares which can help us to predict, but still we need to go for the actual printing because it changes across different machines. It's you have different commercial players for LPBF. So you have to do some test prints and see how it actually works. And before that, you have to do some simulations to make sure that you're getting it right. So anticipate the region where things can go wrong, and then you have to go for the test prints. Yes.
Thank you, sir.
I
Thank
don't
you
know
for
whether I have
taking.
answered their question, so whether they got it cleared. So is that what they were expecting, or?
I hope so. And this is only the question from chat box. And the same person from Ram Krishna, he is asking another one question, sir. How would your mitigation strategy change if the same lattice were produced using electron beam melting instead of LPBF?
See, we don't prefer electron beam printing for primarily for printing. I mean, it's meant for titanium material. So, and also it could be fast, but mostly it's done on vacuum and other things. So the result what we get is not so no, it's not so good, like the roughness and other things. It requires a lot of post processing and other things. So my takeaway is, like, I would say you have to go in for laser based powder bed fusion process. But I've seen a lot of people doing titanium implants in ABM, but it involves a lot of post processing. It's not like LPBF. LPBF is a straightforward thing. So it has got so many advantages than the EPBF.
Yeah. Thank you, sir. Thank you.
So yeah.
Participants have any other questions? You can unmute yourself and ask. And we have another one question from Mr. Anup Krishna.
Yes.
I have to make a hybrid type peak implant, tie outer body. How would go about it?
Sorry, can you just repeat the question again?
Okay, I have to make a hybrid TI, titanium peak implant. So titanium outer body. So how would go about it?
Okay, so you have two different materials, right? PEEK and you have this
Yes, 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 yes.
titanium. So yeah, one is the polymer, the other one is metal. So it's a tricky question. So
And I believe it's not possible in
it's
3D printing.
so one thing you
Because-
can do, you can first try it around this thing. First, you have to print in metal, and then you have to go in for polymer-based printing, like robotic kind of no, polymer printing that you can just think around. First, you have to do it in metal. So
Okay.
once it is done, you have to take and then you need to set. But again, uh, printing it on top of that could be very challenging. So how do you prepare surface for printing and all? So
Mhm. Yeah. Thank you, sir.
Yeah.
Is there any question from audience side? Okay, another question from Amit Soni. Future challenges of additive manufacturing in healthcare application. I think the person is asking what is the future challenges.
Challenges. It's like so it's latticing can see. So a lot of us, I'm from software side. What challenges I will tell, like so we are trying to come up with customized lattice printing. So how do we come up with new sets of unit cell creations apart from the things that are available in the existing researches? So how do we come up with a new design? So how do we validate that? So those kind of things. And in implants, you have this concept called stress shielding. So how do we uh, reduce the bone losses by going with the customized plants? That has been a big challenge. So how do we go around that? That is it. How we can reduce that? We should not remove too much of bone losses should not be there. So how we can prevent that? That we can just think. And the material. So that is a very big concern that we have. There are not much materials in 3D printing. So a lot of research works is going in the material aspects, especially in metals. So we have very limited materials, and people when they come up with no a new material, if they ask us to test or if they want to do some printing and other things, it is very challenging. So what process parameters that you define for printing, it has been a very big issue. And again, we have found a solution for do that also. So we have a software called AIM Optimat, so which can help in coming up with this process parameters. It helps to uh, anticipate what process parameters that you could use, what process parameters combinations like laser power, scan speed, head spacing, and so on across different regions like core, contour, pre-contours, and post-contours, and so on. Yes, and also supports. How do we go around the supports? Like how we can minimize it, how we can print without support structures. So those kind of things are there.
Thank you, sir. This is a new information for us also. And another question from Dr. K. Gobi Saravanan, our center head. And he's asking which kind of lattice structure will give better mechanical properties?
Okay, so I think we have shown some case studies like so we have discussed about a lot of case studies here, right? So people have done some comparisons. So these are some results that you could see, like so I could say based on the literatures. So I'm not from the application side. I'm mostly on the software side. So I'm not able to see the exact lattice that is no, that could be the best option to go for. So right now I don't have an answer for it because, as I said, I'm not from the application side. I'm mostly from the software side. Yes.
Yes, thank you, sir. I think this is the final question. And another one question, I think this is the one final. Sir, we can use peak material for thermal application like pulsating heat pipe.
Yeah. Yes, you can use this.
Mhm. Oh, in this, when we need a very less heat producing agent or heat sink, in that place, is it possible to use peak material, sir? Especially in pulsating heat
See,
pipe.
I have to think about this because I'm from metal. It's okay. So I'm into
Okay.
metals. So these are related to this polymers and other things. So yeah.
Yeah.
So if you any questions related to metals, I will be able to happy to
Okay.
answer. Yes.
Yeah, sure. What about ceramic materials?
Ceramics is also a bit new to us because in LPBF mostly we focus on metals.
Okay.
So any questions in metals would be good because these are something that I have to check in internet and then I have to get back. So
Yeah, thanks. Actually, the participants are writing a questions. I think due to some time limitation, we can end up the section here. Participants have any questions, you can feel free to write to our email ID, which is mentioned in the flyer, so that we can contact you separately. Thank you, sir. Thank you very much.
yeah,
And thank you
thanks.
once again
Thank you.
for your
Thank you.
questions and very informative session also, sir. Thank you,
Yeah.
sir.
Yeah. Thank you. Bye.
Thank you.
Bye.
We are waiting for the next resource person. The session will start in within few minutes.